Alright, so in this lesson we're going to specifically look at some applications of centripetal force, and we're going to look at the circular orbit due to gravity as the primary application of uniform circular motion that we're going to look at in this lesson. So there are many situations that can be modeled as uniform circular motion. Circular orbit due to gravity, a car moving around a curve, an object being swung in a circle by a rope or a chain. We can use our knowledge of forces to determine what is going on in these types of situations. And I would say in lots of cases, drawing a free body diagram is a good first step. So let's look at a circular orbit in particular. And so if you have something that's orbiting around a planet or a star or a moon, gravity is the force that's primarily responsible for holding an object in that orbit. We can actually use Newton's law of gravity, G mm over r squared, and set that equal to the centripetal force mv squared over r. Now in this case, the little m is the mass of the satellite or space station here. The big M is the mass of the planet. The capital G is the universal gravitational constant, and r is the radius of that orbit. It's actually measured from the center of the planet, not the surface of the Earth, or the surface of the planet. So if we do some quick algebra, we can divide the mass of the satellite out and divide one of your radius, or one of those radii out, and we get really that the speed that you need to be in an orbit is related to only three things: the universal gravitational constant, the mass of the planet or object you want to orbit around, and the radius of your orbit. In fact, if we calculate what the orbital speed is in a circular orbit, we'd have the square root of gm over r. So let's do a quick example problem. I've looked up where the Hubble Space Telescope is, and so the Hubble Space Telescope is a telescope that we've put, obviously, in space. It's probably one of the largest telescopes that we've built. The advantage to putting a telescope in space is that you have no atmosphere to distort the view that you have of the skies, and so you can get very nice pictures from the Hubble Space Telescope that you could never get from a telescope here on Earth. The Hubble Space Telescope orbits at a height of 598 kilometers above the Earth's surface, and so what we want to do is figure out what is the orbital speed of the Hubble Space Telescope, assuming that it's in a circular orbit. So the first step we're going to do is we're going to do square root of gm over r as the orbital speed. Some things that I know the constant g, 6.67 times 10 to the negative 11th. I also know the capital M, what the mass of the Earth is, 5.98 times 10 to the 24th kilograms. Those are two things I could look up. Now it's worth pointing out that r is the radius of the Earth plus the height above the surface of the Earth. We were given just the altitude, or the height above the surface, 598 kilometers. Now the radius of the orbit is obviously bigger than 598 kilometers because the Earth has some radius to it. And so if we look at what the radius of the Earth is, it's 6.38 times 10 to the 6th meters. And so if we add that up, we get 6.98 times 10 to the 6th meters. The radius of the Earth is a little more than 6,000 kilometers. And so when we plug all these numbers in and do our math, we find that the Hubble Space Telescope has to be orbiting the Earth at 7.56 times 10 to the 3rd meters per second, or we could say 7.56 kilometers per second. So this thing's got to be moving relatively fast in its orbit in order to stay up in that circular orbit. So let's find the height above the Earth of a satellite that's in a geosynchronous orbit. The term geosynchronous means that that satellite stays over the same location of Earth at all times, which means that the orbital period of that satellite has to be equal to the period of the rotation of the Earth. So the orbital period must be 1 day. Stays above the same location, so it takes 1 day to orbit the Earth, is what that term means. So we have the square root of gm over r is equal to v. We can also relate v to period, that the speed in a circular orbit is 2 pi r, the circumference of your orbit, divided by the period of that orbit. So here are some things that I know right away. I know g, m, I know the period of 1 day, and I'm really looking for r. So if I set these two equal to one another, I think what I need to do is figure out, well, how do I solve this thing for r? So the first step that I would do is square everything. And so there we got 4 pi squared r squared over period squared is equal to gm over r. And if I do some rearranging and I divide by the 4 pi squared, I'm going to multiply by t squared and r, I would end up with this. So it's worth pointing out is that period squared and radius cubed happen to be proportional to one another. That this actually shows up somewhere else when we look at orbits. What my AP Physics students study as Kepler's laws, that this also works for an elliptical orbit as well as a circular orbit. That the period squared of an orbit is equal to the cube of the radius of that orbit. So we can actually solve this out by cube rooting both sides, or taking both sides to the 1/3 power. And so if I plug in all my numbers, I get that the radius of this orbit would have to be 4.23 times 10 to the 7th meters. Or what is that, 42,000 kilometers, something like that. So you might ask, why would we want to do this? And there are several reasons why we might want to put a satellite in a geosynchronous orbit. And there are several types of satellites that I can think of that are in this type of orbit. One of them is weather satellites that we use to take pictures of clouds. We want to know what are the cloud formations over, say, the eastern Pacific Ocean at any given point in time. We want to be able to see that picture in time lapse, see the motion of those cloud systems. Having a geosynchronous satellite that sits over, well, the eastern Pacific Ocean would be a good way to do that. Communication satellites are another one. If you get satellite television, you don't have to go and adjust the direction your satellite points each day to get the satellite signal from space. Your satellite receiver is adjusted to a particular position to point at a satellite somewhere in a particular geosynchronous orbit. The third type of satellite that I can think of is a spy satellite. There are obviously some nations that would like to have a 24/7 view of another nation or a part of another nation. For the United States, some countries that we might be very interested in watching 24 hours a day, 7 days a week, would be places like Iran or North Korea or Russia. Might be countries that we would be interested in looking at all the time to see what's happening as things progress. Now, of course, one disadvantage is 42 or 4.23 times 10 to the 7th meters, or 42,000 kilometers away, is a long ways away. So you'd have to have a pretty good camera in order to see what's happening at that distance, especially if you want to look at something very detailed. So that's kind of a quick overview of circular orbits. Oh, there, we figured out the height above the Earth. Sorry, I wanted to say the height above the Earth. The 4.23 times 10 to the 7th is the radius of the orbit. It's actually only 35,000 kilometers above the Earth, not 42,000. So that would be your circular orbits. Now, we can start to look at in the next lesson is we'll start to look at how we deal with objects that are traveling on a curve, say a car driving around a curve, and how we can apply this idea of uniform circular motion to that type of situation.